The James Webb Space Telescope was designed not merely to confirm established cosmological models, but to rigorously test their validity through observations of the early universe at unprecedented depth and resolution. Since achieving first light in 2022, JWST has extended the observational frontier, probing epochs previously inaccessible to instruments such as the Hubble Space Telescope. Early findings indicate significant tension with predictions derived from the Lambda CDM model, particularly regarding the rapid emergence of massive, chemically evolved, and morphologically complex galaxies within the first few 100 million years after the Big Bang. The Hubble tension, a long-standing discrepancy in measurements of the universe's expansion rate, has not been resolved by Webb's precision measurements. It has been confirmed as real, pointing toward physics the Standard Model does not contain. The story of how the universe came to be is not wrong in its broad outlines, but in its details, in the rates, the timescales, the mechanisms, it appears to be substantially incomplete. What follows is the most rigorous account of what Webb has actually found, what it means, and how much we do not yet understand. The Standard Model before Webb. To understand what Webb has disrupted, it is necessary to first understand what it disrupted. The Lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, is the theoretical framework that has governed cosmology for roughly 3 decades. It is one of the most successful scientific models in history by any standard measure. It correctly predicts the large-scale structure of the universe, the statistical distribution of galaxies across cosmic time, the pattern of temperature fluctuations in the cosmic microwave background, and the proportions of hydrogen and helium produced in the first few minutes after the Big Bang. It is not a speculative framework. It is a quantitatively precise, extensively tested, and broadly confirmed description of how the universe is structured and how it evolved. When cosmologists refer to the Standard Model of cosmology, they mean Lambda CDM, and they invoke it with the same confidence that particle physicists mean when they invoke the Standard Model of particle physics, a framework so thoroughly tested that the community has implicitly accepted it as the correct description of reality at the scales it covers. The model begins with the Big Bang approximately 13.8 billion years ago, when the observable universe was compressed into an extraordinarily hot and dense state. In the first fractions of a second, the fundamental forces of physics separated from a unified high-energy state into the distinct forces observed today. In the first 3 minutes, nuclear fusion produced the primordial ratio of hydrogen to helium, approximately 3:1 by mass, along with trace amounts of lithium and deuterium. This primordial nucleosynthesis is one of the most precisely confirmed predictions in all of physics. The abundances of these light elements, measured in old chemically unprocessed stars and in the diffuse gas of intergalactic space, agree with theoretical predictions to within a few percent across multiple independent methods and instruments. That agreement is not circular. It is a quantitative prediction that the universe had to satisfy, derived from first principles of nuclear physics applied to the conditions of the early universe, and the universe satisfies it. The success of primordial nucleosynthesis is among the strongest evidence that the Big Bang description of the first minutes of cosmic history is correct in its essential physics. For the next 380,000 years after the Big Bang, the universe was opaque. The temperature was so high and the density so extreme that photons could not travel freely. They were constantly scattering off free electrons in the hot plasma, bouncing between charged particles like light trapped in a dense glowing fog. The universe was not dark during this period. It was intensely luminous. But the mean free path of a photon, the average distance it could travel before scattering off a free electron, was far smaller than the observable horizon. No information could propagate across meaningful distances. When the temperature dropped to approximately 3000 Kelvin, roughly 380,000 years after the Big Bang, protons and electrons combined into neutral hydrogen atoms for the first time through a process called recombination. The moment recombination occurred, the photons that had been trapped in the plasma were suddenly free to propagate unimpeded in all directions. That radiation, stretched by 13.8 billion years of cosmic expansion from its original temperatures into the microwave band, is the cosmic microwave background, the oldest light in the observable universe, detectable today as a nearly uniform glow of microwave radiation filling the sky in every direction. Its existence was first predicted theoretically in the late 1940s and detected by accident in 1964 by Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics for their discovery. The tiny temperature fluctuations in the cosmic microwave background, variations at the level of 1 part in 100,000 in the temperature of this ancient light across different directions on the sky, represent the density variations in the early universe that grew under gravity into the galaxies and large-scale structures observed today. These fluctuations were mapped in increasing detail by the COBE satellite in the 1990s, WMAP in the 2000s, and finally with extraordinary precision by the Planck satellite, whose final data release in 2018 provided the most accurate characterization of the cosmic microwave background power spectrum ever achieved. The Lambda CDM model fits the Planck data with remarkable precision. 6 free parameters describing the full statistical pattern of temperature fluctuations across the entire observable universe. This is a profound and genuine scientific achievement. A model with 6 parameters correctly describing the pattern of the oldest light in the universe and correctly predicting from those 6 parameters the large-scale distribution of matter billions of years later is not something to be dismissed when a new telescope finds tensions with its predictions. It is something to be taken very seriously. The growth of those initial density fluctuations into the structures observed today is where dark matter plays its central role. Ordinary baryonic matter, the protons, neutrons, and electrons that constitute everything visible, cannot collapse fast enough under gravity alone to explain the observed structures. In the early universe, baryonic matter was electromagnetically coupled to the photon field, and the radiation pressure of the photons resisted the gravitational collapse of baryonic density fluctuations. This coupling prevented baryonic matter from forming the dense clumps needed to seed galaxies until recombination freed it from the photon field. The resulting structures, growing from small initial fluctuations in only 13.8 billion years, are not massive enough to match what is observed without additional gravitational contribution. Dark matter solves this by providing a gravitational head start. Dark matter interacts gravitationally but not electromagnetically, so it was not coupled to the photon field in the early universe. It could begin clumping under gravity long before recombination, forming the dark matter halos that represent the gravitational scaffolding into which ordinary matter fell after recombination. By the time baryonic matter was free to collapse, the dark matter had already pre-assembled the deep gravitational potential wells needed to concentrate it. The result is the cosmic web, the network of dark matter filaments and sheets connecting massive halos at the intersections, that emerges naturally from Lambda CDM simulations, and that matches the observed large-scale distribution of galaxies with impressive fidelity. Within this framework, galaxy formation follows a hierarchical bottom-up sequence. The smallest dark matter halos collapse first because density fluctuations are statistically stronger on small scales in the Lambda CDM initial conditions spectrum. These first halos are the seeds of small dwarf-like proto-galaxies. Over time, these small systems merge, combine their gas and stellar content, and grow into more massive galaxies. Larger galaxies are therefore younger in a statistical sense. They are built from the accumulated mergers of many smaller predecessors, and their assembly takes time. The central quantitative prediction that follows from this framework is that massive galaxies, those with stellar masses comparable to or exceeding the Milky Way's roughly 60 billion solar masses, should be rare or absent in the early universe because the hierarchical merging process has not had sufficient time to assemble them. The early universe should be populated primarily by small, irregular, low-mass protogalactic clumps, with the large, morphologically regular, stellar mass-rich systems emerging only after several billion years of progressive assembly. Hubble's observations broadly confirmed this picture within its capabilities. The farthest galaxies Hubble could characterize in detail were small, irregular, and low in stellar mass, consistent with the expected early universe population. The larger, more mature systems appeared at lower redshifts, in rough agreement with the hierarchical timeline. The missing observational window was the very early universe, redshifts above 7 or 8, corresponding to the first 700 million years, where Hubble lacked the infrared sensitivity to see the faint, redshifted light of the galaxy population. Webb was built to fill exactly that window, and what it has found there is not consistent with the extrapolation of the standard model that Hubble's observations supported. Why infrared changes everything. The design of Webb as an infrared telescope was dictated by the physics of the expanding universe and by the specific observational challenge of studying objects at the greatest accessible distances. Appreciating why requires understanding what the expansion of space does to the light that travels through it, and what that means for the wavelengths at which the most distant objects can be seen. The universe is expanding. This is not motion of galaxies through pre-existing space in the way that an explosion propels debris outward. It is the expansion of the space between galaxies, the stretching of the space-time fabric itself. The practical consequence for observational astronomy is that the wavelength of any photon traveling through this expanding space increases as the space expands. A photon emitted by a distant galaxy as ultraviolet light at a wavelength of 0.1 micrometers arrives at Earth with a longer wavelength determined by how much the universe has expanded during the photon's travel time. For a galaxy at a redshift of 10, the universe has expanded by a factor of 11 since the photon was emitted, and the photon arrives with a wavelength 11 times its original value, at 1.1 micrometers in the near-infrared. For a galaxy at a redshift of 14, the stretch factor is 15, and a photon originally emitted at 0.1 micrometers arrives at 1.5 micrometers. For the most distant objects Webb is characterizing, essentially all of the galaxy's emitted light, regardless of its original wavelength, arrives at Earth in the infrared. Hubble's most sensitive detectors operated in the ultraviolet and visible wavebands, from about 0.2 micrometers to roughly 1 micrometer, with limited infrared capability through the wide-field camera 3 extending to about 1.6 micrometers. At a redshift of 6, light originally emitted at 0.12 micrometers. The Lyman break wavelength that is the primary photometric redshift indicator for high redshift galaxies arrives at 0.84 micrometers within Hubble's visible range. At a redshift of 8, the same feature arrives at 1.08 micrometers, at the edge of Hubble's near-infrared sensitivity. At a redshift of 10, it arrives at 1.32 micrometers, where Hubble's sensitivity had declined substantially. Beyond redshift 10, the key spectral features of galaxies had redshifted entirely beyond Hubble's reach, and the telescope was essentially blind to the normal population of galaxies at those distances. This limitation was not merely a matter of sensitivity, of whether Hubble could detect an object at all. It was a matter of physical characterization. A galaxy barely detectable at the edge of Hubble's sensitivity cannot have its stellar population, star formation rate, chemical composition, or morphology characterized with any reliability. The scientific questions: how massive is this galaxy? How old are its stars? How fast is it forming new stars? Does it contain interstellar dust? Require signal-to-noise ratios far above the detection threshold. Hubble's high redshift galaxy science was therefore limited to the brightest, most exceptional objects at redshifts above 8, and the physical characterization of those objects was crude by the standards of what was needed to test galaxy formation models quantitatively. Webb's near-infrared camera covers wavelengths from 0.6 micrometers to 5 micrometers, and does so with a primary mirror of 6.5 meters diameter, a light collecting area roughly 6 times larger than Hubble's. The detector arrays achieve a sensitivity and wavelength range that allows the detection and characterization of galaxies at redshifts up to 15 and beyond, accessing look-back times of 13.6 billion years and observing the universe when it was only 300 million years old. The near-infrared spectrograph can simultaneously obtain spectra of hundreds of objects in a single pointing, measuring redshifts and physical properties, emission line ratios, gas metallicities, stellar velocity dispersions, for large samples rather than one object at a time. The mid-infrared instrument extends coverage to 28 micrometers, accessing the thermal emission from warm interstellar dust in high redshift galaxies, and revealing star formation activity hidden behind dust screens that are opaque to all shorter wavelength instruments. The dust penetration advantage of infrared observations adds a systematic improvement to the galaxy census that goes beyond the simple redshift argument. Star-forming galaxies in the early universe are not transparent. They contain interstellar dust, tiny particles of silicates and carbonaceous material produced in the winds of evolved stars and dispersed by supernova ejecta that absorbs ultraviolet and short-wavelength visible photons far more efficiently than it absorbs longer wavelength infrared photons. A galaxy forming stars at a high rate behind a substantial column of interstellar dust appears faint and red in ultraviolet and optical observations. It might be missed entirely in surveys that require optical detections as a prerequisite for inclusion. This dust bias means that pre-Webb surveys, which were primarily optical or limited-range infrared, systematically undercounted the most actively star-forming galaxies in the early universe and underestimated the total star formation rates of the galaxies they did detect. The correction for this bias, now measurable for the first time with MIRI's mid-infrared sensitivity, is substantial. Estimates of the total star formation rate density in the early universe have been revised upward by factors of 2 to 5 in some redshift ranges based on Webb data. The combined effect of Webb's infrared wavelength coverage, its primary mirror size, its detector sensitivity, and its spectroscopic multiplexing capability is not an incremental improvement over Hubble. It is a qualitative transformation of what is observable. With Hubble, the high redshift universe was a frontier where a few dozen exceptional objects could be detected and crudely characterized. With Webb, it is a well-sampled domain where thousands of objects can be detected, hundreds can be spectroscopically confirmed, and their physical properties can be measured with enough precision to test galaxy formation models quantitatively. The early universe is no longer mostly inaccessible. It has been opened, and what is inside it is not what the models expected to find. The first deep fields. Within months of beginning science operations in 2022, Webb released its first deep field observations. Long infrared exposures of small patches of sky designed to reach the faintest and most distant objects accessible to the instrument. The first public release pointed at the galaxy cluster SMACS 0723, approximately 4.6 billion light-years away, using the cluster's gravitational mass as a natural telescope. A sufficiently massive object, a galaxy cluster containing trillions of solar masses of matter, bends and focuses the light from background galaxies, even more distant than the cluster itself, amplifying their apparent brightness through gravitational lensing. The SMACS field used this amplification to push deeper than would have been possible with direct observation, revealing background galaxies at redshifts that had been inaccessible to prior instruments. The total exposure time was 12.5 hours across multiple near-infrared filters, and the resulting image covered a patch of sky the size of a grain of sand held at arm's length, a tiny fraction of the celestial sphere. Within that tiny patch, thousands of galaxies appeared at distances spanning the full range from the nearby universe to the cosmological horizon. The systematic scientific programs that followed the initial public release were designed for quantitative analysis rather than demonstration. The JADE survey, the JWST Advanced Deep Extragalactic Survey, was among the most ambitious, combining the deepest NIRCam imaging Webb has yet obtained with spectroscopic follow-up for thousands of individual galaxies using the near-infrared spectrograph. JADES targeted two fields: the Hubble Ultra-Deep Field, the most heavily observed patch of sky in the history of astronomy with over 1 million seconds of accumulated Hubble integration time, and an adjacent field called the JADES Origin Field. In both regions, Webb's infrared sensitivity added a dimension that all prior observations had lacked, detecting galaxies in the first 500 million years of cosmic history at number densities that allowed statistical comparisons with model predictions for the first time. The CEERS survey, the Cosmic Evolution Early Release Science Survey, covered a larger area at shallower depth, providing the statistical sample of galaxies across a broader redshift range needed to measure the galaxy luminosity function and stellar mass function at different epochs. These functions, the number of galaxies of different brightnesses and masses per unit volume of space at each cosmic time, are the primary observational constraints on galaxy formation models. Their accurate measurement requires large, representative samples without strong selection biases, and CEERS provided the first such samples from Webb data at redshifts above 6. The comparison between the CEERS measured luminosity function at redshift 8 and the predictions of a broad suite of Lambda CDM simulations published by Finkelstein and colleagues in 2023 showed an excess of bright, massive galaxies at the level of 10 to 100 times the predicted number density, depending on the luminosity range examined. This excess was statistically robust, present across independent analysis teams, using different photometric redshift codes and different stellar population models, and not attributable to any identified systematic error in the data. The galaxy number excess was concentrated at the bright end of the luminosity function, the most massive, most luminous objects, while the faint end agreed more closely with model predictions. This pattern is physically informative. The Lambda CDM model's predictions are most uncertain at the bright end, precisely because of the feedback physics that is least well constrained. The processes by which supernovae, stellar winds, and active galactic nucleus outflows expel gas from forming galaxies and limit the conversion of gas into stars. The faint end of the luminosity function, populated by lower mass galaxies where feedback is less extreme, is better reproduced. The systematic failure at the bright end points specifically to the feedback physics being wrong, either too efficient in suppressing star formation in massive galaxies, or applied on the wrong timescales, or both. The photometric redshifts on which most of the statistical sample was based were subject to the concern that some apparent high redshift galaxies might actually be lower redshift objects with unusual colors that mimic the high redshift photometric signature. This contamination would inflate the apparent number of high redshift galaxies, potentially explaining some of the excess over-model predictions as a statistical artifact rather than a physical signal. The extensive spectroscopic follow-up programs within JADES addressed this concern directly by obtaining spectroscopic redshifts, precise, model-independent distance measurements based on identified spectral emission and absorption lines for a large subset of the photometric sample. The spectroscopic confirmation rate among the brightest photometric high redshift candidates was high, typically above 70%, and the confirmed spectroscopic redshifts agreed well with the photometric estimates. The contamination by lower redshift interlopers was present, but at levels too low to explain the observed excess. The deep field results were confirmed. The early universe contained more massive, more luminous galaxies than Lambda CDM predicted, and the signal was real. The deep field data also revealed structure in the early universe that was unexpected in its scale and maturity. Rather than being distributed randomly across the survey fields, the high redshift galaxies clustered into dense protoclusters, overdense regions containing 10 to 50 galaxies within projected distances of a few megaparsecs, with individual members showing the enhanced star formation rates and disturbed morphologies characteristic of dense environments. One particularly striking protocluster, identified in the JWST data at a redshift of approximately 7.7, contained more than 10 spectroscopically confirmed members within a physical volume smaller than what is typical for such structures at much lower redshifts. Its existence at this epoch and its physical compactness implied that large-scale structure was assembling faster than Lambda CDM simulations predicted, that the seeds of today's massive galaxy clusters were already forming when the universe was less than 700 million years old, earlier and more efficiently than the models described. The red monsters. Among the discoveries from Webb's first years of operation, the objects informally called red monsters generated the most immediate tension with the standard model of cosmology and the most intense subsequent theoretical debate. The informal name was applied by the scientific community and subsequently the media to a specific population of galaxies found at high redshifts, seen when the universe was between roughly 500 million and 800 million years old, whose infrared colors were extraordinarily red and whose implied stellar masses, derived from detailed modeling of their spectral energy distributions, placed them at or above the stellar mass of the present-day Milky Way at epochs when the hierarchical assembly model predicts such masses to be essentially absent. Understanding what makes their redness physically significant requires understanding what the multiband infrared photometry from Webb actually measures and what it implies about the physical conditions within these galaxies. Webb's NIRCam observes galaxies through a series of filters covering different narrow wavelength ranges from 0.6 micrometers to 5 micrometers. The flux detected through each filter reflects the amount of light the galaxy is emitting at the corresponding rest frame wavelength, after accounting for the cosmological redshift that shifts all wavelengths by the same factor. By comparing the fluxes in different filters, astronomers reconstruct the spectral energy distribution of the galaxy, a curve showing how the galaxy's light output varies with wavelength in its rest frame. The shape of this curve carries information about the stellar population. Hot, young, massive stars produce most of their light in the ultraviolet. Cooler, older, lower mass stars produce more light in the red and infrared. Dust-heated emission produces a distinctive rise in the mid-infrared. Fitting theoretical stellar population models to the observed spectral energy distribution extracts the combination of ages, masses, metallicities, and dust contents that best reproduces the observations. The red monsters have spectral energy distributions that fall in a part of parameter space that the standard model did not anticipate being populated at their redshifts. Their rest frame optical colors, the part of the spectrum that would appear as yellow and red visible light if the galaxy were nearby, are redder than the typical galaxy at any redshift. This can be produced by three distinct physical conditions, which the models attempt to distinguish. Old stellar populations, where the blue massive stars have exhausted their fuel and the remaining stellar light is dominated by cooler, redder evolved stars. Heavy dust attenuation, where interstellar dust absorbs the blue light and re-radiates it in the infrared. Or the contribution of emission from an active galactic nucleus, whose spectral energy distribution differs systematically from that of a normal stellar population. In practice, many of the red monsters show evidence for more than one of these conditions simultaneously, which complicates the stellar mass estimation but does not change the fundamental physical conclusion that these galaxies are massive. The tension with Lambda CDM was quantified most precisely in the 2023 Nature paper by Lubber and colleagues, who analyzed 6 galaxies in the Sears survey field with photometric redshifts between 7 and 10 and stellar masses between several tens of billions and approximately 100 billion solar masses. The cumulative stellar mass density implied by this small sample, the total mass of stars per unit volume of the universe at those redshifts, was compared to the predictions of multiple state-of-the-art cosmological simulations, including Illustris Tongue, Eagle, and FLARES. The observed stellar mass density at redshift 8 exceeded all simulation predictions by factors ranging from 10 to 100. The paper used an analogy that captured the essential strangeness for a general scientific audience. Finding a galaxy with the stellar mass of the Milky Way at a redshift of 8 is like finding a fully grown adult who is only 6 months old. The physical processes that build stellar mass have known speed limits, and the red monsters appear to have broken them. Subsequent spectroscopic follow-up of the Labe candidates with NARSPEC confirmed the high redshifts of several objects and provided the first direct constraints on their physical conditions. Spectra revealed emission lines characteristic of ionized gas, hydrogen Balmer lines, oxygen forbidden lines, nitrogen emission, whose ratios encode information about the ionization state of the gas and, by inference, the nature of the ionizing radiation source. Several of the spectroscopically confirmed candidates showed emission line ratios inconsistent with pure stellar photoionization and more consistent with a significant contribution from an active galactic nucleus. This finding opened the possibility that the stellar mass estimates were inflated by active galactic nucleus light, contaminating the photometric fitting. Revised stellar mass estimates incorporating active galactic nucleus corrections were lower for the affected objects by factors of 2 to 5, bringing the most extreme outliers somewhat closer to model predictions. But even after correction, multiple objects in the sample retained stellar masses, well above the model predictions for their redshifts, and the overall stellar mass density remained substantially elevated above the simulations. The physical implications are demanding regardless of the correction. For a galaxy to accumulate 60 billion solar masses of stars by a redshift of 8, a more conservative version of the red monster claim after active galactic nucleus corrections, it must have maintained average star formation rates of approximately 100 solar masses per year for 600 million years, assuming star formation began immediately after the Big Bang and proceeded continuously. The present-day Milky Way forms stars at 2 to 3 solar masses per year. The most intensely star-forming galaxies in the present-day universe, the so-called sub-millimeter galaxies discovered in far infrared surveys, form stars at several hundred to perhaps 1,000 solar masses per year, and are rare enough to be counted in the dozens across the entire sky. The red monsters apparently required star formation intensities comparable to the most extreme present-day systems, but sustained not briefly but over hundreds of millions of years, in a universe whose gas supply was less enriched, less pre-processed, and less efficiently delivered to galaxy-scale halos than present-day conditions permit. The Standard Model's galaxy formation physics, as currently implemented, cannot accommodate this. The problem of cosmic time. The red monsters crystallize a problem that runs through all of Webb's early universe observations. The universe apparently did not have enough time to build what Webb is finding, given the physical processes the Standard Model describes as governing its evolution. This problem is not unique to the most extreme objects. It applies in varying degrees across the full range of anomalies Webb has identified, and its resolution, if one exists within the Lambda CDM framework, requires either revisions to the specific physics of galaxy formation and star formation as currently modeled, or modifications to the initial conditions of structure formation, or both. The fundamental rate-limiting process for building stellar mass is the conversion of gas into stars, and this conversion rate is set by a combination of gas supply, gas cooling, and stellar feedback. Gas must first be accreted onto a dark matter halo from the surrounding intergalactic medium. The accretion rate is limited by the growth rate of the halo, which is set by the statistics of dark matter density fluctuations in the initial conditions of the universe. For the most massive halos in the early universe, those massive enough to host galaxies with tens to hundreds of billions of solar masses of stars, the accretion rates needed to supply enough gas for the observed star formation are at or near the theoretical maximum permitted by the Lambda CDM initial conditions. This means the models cannot simply increase the gas supply to solve the problem. The supply is already running at maximum capacity under the standard framework. Once gas is accreted, it must cool from the virial temperature of the dark matter halo, the temperature at which the infalling gas is shock heated as it enters the halo, down to the temperatures at which hydrogen can form molecules and then stars. For massive dark matter halos at high redshift, the virial temperatures reach tens of millions of Kelvin. Cooling gas from these temperatures to the tens of Kelvin needed for molecular cloud formation takes time, and the dominant cooling mechanisms, line emission from metal ions and molecules, are less efficient in metal-poor primordial gas than in the metal-enriched gas of lower redshift galaxies. The cooling timescale for primordial gas in a massive early halo is not negligible relative to the Hubble time at that epoch, adding to the list of processes that must complete rapidly within an already compressed timeline. After cooling, the gas must fragment into molecular clouds and then into individual star-forming cores. The rate at which molecular clouds convert to stars is limited by stellar feedback. The radiation, winds, and supernova explosions of already formed stars that heat and disrupt the surrounding gas, limiting the star formation efficiency to a few % per freefall time in present-day observations. If early universe galaxies formed stars with the same efficiency as present-day galaxies, they would not be able to accumulate stellar masses at the rates Webb implies. Some theorists have proposed that early universe conditions, lower gas metallicity reducing the effectiveness of radiative feedback, higher gas densities reducing the free-fall time, more compact galaxy sizes reducing the escape of ionizing radiation, might permit higher star formation efficiencies than in the present-day universe. This is physically motivated, but the required efficiency enhancements are large, factors of several above present-day values, and implementing them consistently with all other observational constraints on galaxy properties is not straightforward. The chemical enrichment evidence adds the most precise constraint on the timing problem. Spectroscopic observations of early galaxies by Webb have now detected oxygen emission lines in galaxies at redshifts above 12, corresponding to ages of the universe below 400 million years. Oxygen is one of the most abundant heavy elements produced by stellar nucleosynthesis. It is synthesized in the cores of massive stars and expelled into the interstellar medium when those stars die as core collapse supernovae. Its presence in the spectrum of a galaxy at a very high redshift means that the complete cycle of stellar evolution, gas to stars, stars evolving on the main sequence, stars exploding as supernovae, ejecta mixing into the interstellar medium, had already completed before the observation epoch. Massive stars above approximately 8 solar masses live for between 3 million and 30 million years before exploding. The supernova ejecta mix into the surrounding gas on timescales of tens of millions of years. For oxygen to be present in the interstellar medium of a galaxy at 350 million years after the Big Bang, the first stars must have formed by approximately 200 million years after the Big Bang at the latest, allowing time for evolution, explosion, and mixing. JADE's GSZ140, spectroscopically confirmed by Webb at a redshift of 14.32 and currently the highest redshift galaxy with a confirmed spectroscopic redshift, is seen when the universe was approximately 290 million years old. Its spectrum shows oxygen emission, implying that stars had already formed and died in this galaxy before this epoch. The constraints on the timing of first star formation in this system push back to perhaps 150 to 200 million years after the Big Bang, within the first 1% of the universe's current age. Lambda CDM models do predict that the first stars, formed from primordial gas in the smallest dark matter halos, began forming between 100 and 200 million years after the Big Bang, so this is not an immediate contradiction. But the efficiency of chemical enrichment implied by the oxygen abundance in JADE's GSZ140, how much oxygen has been produced relative to the total available primordial gas, is at the upper end of what even optimistic models predict for this epoch. The universe's earliest galaxies were enriching their interstellar media with heavy elements at rates that leave little room for inefficiency. The combined constraints, stellar mass, gas supply, cooling, star formation efficiency, and chemical enrichment timescales, do not demonstrate that the Lambda CDM model is fundamentally wrong. They demonstrate that the specific physics implementations used in current galaxy formation simulations are not reproducing the observed properties of the early universe. This is a meaningful distinction. The Big Bang cosmology, the cosmic microwave background, the large-scale structure of the universe. These are observational facts embedded in the Lambda CDM framework that will not be displaced by Webb's findings. What Webb is showing is that the modeling of the physical processes operating within that framework, how gas cools, how efficiently it forms stars, how strongly stellar feedback limits that formation, needs substantial revision. The revision required is large enough that it will not be accomplished by minor parameter adjustments. It will require new physics of some kind. The little red dots. Among all the novel populations identified in Webb's deep field observations, the objects known as little red dots present the most unresolved interpretive challenge, unlike the red monsters, whose anomaly is primarily one of excessive stellar mass at early epochs. Little red dots are anomalous in multiple simultaneous properties: their number density, their spectral characteristics, their compactness, and the implied masses of the objects at their centers, none of which fit neatly into any existing class of astrophysical object. They were identified as a distinct population in 2023 as researchers noticed a statistically significant population of extremely compact, very red sources scattered across Webb's deep fields at redshifts from roughly 3 to 9, and their characterization has dominated a substantial fraction of the observational and theoretical effort in high redshift galaxy science since their discovery. The basic observational properties of little red dots are by now well established from multiple independent analyses. They are compact, the majority are unresolved or only marginally resolved even in Webb's NARCAM imaging, which achieves angular resolutions of 0.06 to 0.08 arcseconds at near-infrared wavelengths. At a redshift of 5, this angular resolution corresponds to a physical scale of approximately 400 parsecs, roughly 1,300 light-years. A galaxy that is unresolved at this scale has an effective radius smaller than the half-width of the Orion star-forming complex in the Milky Way, an almost inconceivably small physical size for a system that, based on its luminosity, contains enormous amounts of mass. They are red, significantly redder in their rest frame optical colors than the typical galaxy at any redshift, with the redness extending from near-infrared to mid-infrared wavelengths, in a pattern that the standard dust attenuation laws for star-forming galaxies do not reproduce without invoking unusual dust geometries. And they are numerous. Their number density per unit volume of the universe at redshifts between 4 and 7 exceeds the predictions of every published galaxy formation model and every published quasi-luminosity function by factors ranging from 10 to 100. The spectroscopic properties of little red dots are what make their interpretation genuinely contested at the level of fundamental physics. Webb's near-infrared spectrograph has obtained spectra of several hundred confirmed little red dots from multiple surveys, and essentially every well-characterized spectrum presents the same combination of features that defies simple classification. The majority of spectra show broad emission lines, the hydrogen-Balmer lines, in particular the H-alpha and H-beta transitions, with full widths at half maximum corresponding to gas velocities of several thousand kilometers per second. Broad lines of this width in the spectrum of an active galactic nucleus arise from gas orbiting or infalling in the deep gravitational potential of a supermassive black hole, close enough to the black hole that orbital velocities are high. The presence of broad lines is, in the conventional interpretation, a signature of an active galactic nucleus. But the same spectra often also show features inconsistent with a pure active galactic nucleus origin. Narrow emission lines from forbidden transitions, doubly ionized oxygen at 500.7 nanometers, singly ionized nitrogen at 658.4 nanometers. Appear with line ratios that sometimes fall outside the range expected for photoionization by an active galactic nucleus, and closer to the range expected for photoionization by a young hot stellar population. Stellar absorption features appear in some spectra, indicating the presence of a significant stellar population contributing to the total emission. The Balmer break, a distinctive spectral feature produced by hydrogen absorption in the atmospheres of intermediate mass stars, is detected in some little red dot spectra, indicating stellar populations with ages of at least a few 100 million years. No simple combination of an active galactic nucleus plus a normal galaxy stellar population reproduces the full observed spectral properties of the typical little red dot. The black hole masses implied by the broad line widths, if interpreted through the standard virial mass estimator calibrated on low redshift active galactic nuclei, are enormous. Many little red dots imply black hole masses of 100 million to 1 billion solar masses, at redshifts where the universe was less than 1 billion years old. The most massive known black holes in the present-day universe, the supermassive black holes at the centers of the most massive elliptical galaxies, which have had 13.8 billion years to grow, reach masses of tens of billions of solar masses. Finding black holes of 1 billion solar masses at an age of the universe of 700 million years implies growth rates that are difficult to reconcile with standard accretion physics. The theoretical maximum rate at which a black hole can grow by accreting gas, the Eddington rate at which the outward radiation pressure of the accreting material balances the inward gravitational pull, allows the black hole mass to double in approximately 45 million years, if maintained continuously. To grow from a stellar mass black hole seed of perhaps 10 to 100 solar masses to 1 billion solar masses at the Eddington rate requires approximately 900 million years, which for a black hole already at 1 billion solar masses at 700 million years after the Big Bang means the seed would have needed to form and begin accreting at Eddington efficiency before the universe was even 100 million years old, with no interruptions over the entire growth period. This is possible but extremely constraining, and it requires the seed black holes themselves to be far more massive than the stellar remnant seeds that standard models produce. A 2024 analysis by Matthey and colleagues, representing the most comprehensive statistical study of little red dots to date, examined over 400 candidates from multiple Webb deep field datasets and found their luminosity function to exceed model predictions by factors of 10 to 100 across the full range of redshifts and rest frame luminosities sampled. The paper identified a characteristic spectral shape, sometimes described as a V-shaped or rising toward red spectral energy distribution in the rest frame optical, that appeared consistently across the population and distinguished little red dots from both normal galaxies and conventional unobscured quasars. This characteristic shape, present in a large fraction of the sample, regardless of redshift or luminosity, suggests that the population is physically coherent, that its members share a common physical property rather than being a heterogeneous mix of unrelated object types that happen to appear similar in photometric surveys. What that common physical property is remains unclear. The leading proposal involves a specific dust attenuation geometry, perhaps a compact dust torus or shell surrounding an extremely dense stellar or accreting system, that produces the characteristic red spectral slope. But no model yet reproduces the observed properties quantitatively, and the abundance of the objects remains unexplained by any current framework. The first galaxies were not what we expected. Beyond the specific anomalous populations, the red monsters and the little red dots, Webb's comprehensive survey of the early universe has revealed that the general population of the first galaxies differs from model predictions in systematic ways that span their most fundamental physical properties. These differences are not confined to the most extreme objects. They appear across the full distribution of galaxy properties at high redshift, in measurements ranging from morphology and structure to star formation rates, to internal kinematics, and they consistently point in the same direction, toward an early universe that was more organized, more massive, and more physically mature than the Lambda CDM framework predicted. The morphological properties of early galaxies are among the most surprising findings from Webb's imaging programs. The Lambda CDM model's hierarchical assembly scenario predicts that the first galaxies should be structurally irregular, clumpy asymmetric aggregations of star-forming regions without the organized disk or spheroidal components that characterize more evolved systems. This prediction follows directly from the assembly mechanism. Systems built by the progressive merging of smaller precursors should retain the disturbed morphologies imprinted by those mergers, and the smooth symmetric structures of mature galaxies. The exponential stellar disks, the centrally concentrated bulges, emerge only after the system has had sufficient time to dynamically relax following its last major merger. The relaxation timescale for a merger remnant is comparable to its orbital crossing time, typically a few 100 million years, which means galaxies undergoing frequent mergers in the first billion years should persistently show irregular, disturbed morphologies. Webb's high-resolution near-infrared imaging has challenged this expectation systematically. Multiple studies analyzing large samples of galaxies at redshifts above 4, seen when the universe was less than 1.5 billion years old, have found that a significant fraction, estimated at between 20 and 40%, depending on the sample selection and the morphological classification method, display disk-like morphologies. The disk classification is based on quantitative measures of galaxy structure, the Cirsic index, which describes how concentrated the light distribution is, the axis ratio, which measures the elongation of the galaxy's projected shape, and the smoothness and symmetry of the surface brightness profile. Galaxies that score as disks on these measures have light distributions consistent with rotationally supported systems, rather than the pressure-supported irregular structures expected from the hierarchical model at these redshifts. The existence of organized disks in the early universe implies that some galaxies managed to settle into dynamically cold, rotationally supported configurations far faster than current models predict. The settling timescale in simulations, the time required for a merger-disturbed system to relax into a smooth disk, is typically several 100 million years. For galaxies observed with disk morphologies at redshifts of 7 or 8, when the universe is only 700 to 800 million years old, the available time since the Big Bang is barely sufficient for even one complete settling cycle after a major merger. The observations imply either that these galaxies experienced far fewer major mergers than the hierarchical model predicts, perhaps because they resided in underdense environments where merger partners were scarce, or that the disk settling process is substantially faster in the early universe than current simulations reproduce. The NIRSpec spectroscopic follow-up of morphologically classified disk galaxies at high redshift has added kinematic confirmation for a subset of objects, measuring the velocity fields of ionized gas through the Doppler shifting of emission lines across the galaxy's face. Galaxies with ordered rotation, where gas on one side of the galaxy moves toward the observer and gas on the other side moves away in a pattern consistent with a spinning disk, confirm the morphological disk classification with an independent physical measurement. Several such rotationally supported systems have been confirmed at redshifts above 5, with rotation velocities of 200 to 300 kilometers per second, comparable to the rotation velocity of the Milky Way's disk, at epochs when the universe was less than 1 billion years old. The existence of dynamically settled, rapidly rotating disk galaxies at these early times is not predicted by any current version of the Lambda CDM model without invoking specific physical conditions: rapid gas accretion along cold cosmic filaments, efficient angular momentum conservation during infall, that are not well established observationally. The star formation rate properties of the general early galaxy population also show systematic discrepancies from model predictions across the full luminosity range. The specific star formation rate, the star formation rate per unit stellar mass, which measures how efficiently a galaxy is turning its existing stellar content into new stars, is elevated in early galaxies relative to lower redshift analogues at the same mass. This elevation is expected to some degree in the Standard Model, because the early universe had more available gas relative to stellar mass, and higher gas fractions drive higher star formation efficiencies. But the magnitude of the elevation observed by Webb is larger than the models predict, suggesting that the physical processes regulating star formation in early galaxies are operating differently than in present-day galaxies, with higher efficiencies and lower suppression by feedback mechanisms. The systematic nature of this discrepancy, present across 3 orders of magnitude in stellar mass and across the full redshift range from 4 to 10, indicates that it reflects a real physical difference in early universe galaxy formation physics rather than a selection effect or measurement artifact. Early mergers and cosmic structure. The Lambda CDM model's hierarchical structure formation scenario predicts not just the properties of individual galaxies, but the rate and character of the interactions and mergers between them. Galaxy mergers are the engine of hierarchical assembly. Without them, the small protogalactic fragments of the early universe cannot grow into the massive systems observed today, and the model makes specific quantitative predictions about when merger rates peak, how the merger rate depends on galaxy mass and redshift, and what the physical signatures of merging systems look like in observational data. The standard prediction places the peak of major merger activity at redshifts of roughly 2 to 3, corresponding to when the universe was between about 2 and 3 billion years old. At this epoch, the dark matter halos hosting galaxies had grown massive enough to contain substantial gas reservoirs. The galaxy number density was high enough that close encounters were frequent, and the conditions for gas-rich major mergers, the most violent and transformative kind, were maximized. At earlier epochs, the individual galaxies were expected to be less massive, their separations larger relative to their sizes, and the major merger rate correspondingly lower. The very early universe, at redshifts above 6, was supposed to be a time of accretion and gradual assembly, not violent major mergers. Webb's observations have found merging and interacting systems at substantially earlier epochs than this picture predicts. One of the most striking early examples was the detection of a quintet of galaxies in the process of mutual gravitational interaction at a redshift corresponding to a universe age of only a few 100 million years. The system showed tidal features, elongated bridges of stars and gas connecting the interacting members, distorted outer isophotes reflecting the gravitational perturbation of the passage, that are the morphological signatures of ongoing gravitational interaction. Tidal features of this kind are produced when the tidal forces between 2 galaxies overcome the self-gravity of their outer regions, drawing material into elongated streamers along the direction of the encounter. Their visibility in Webb's imaging confirms that the system is in the process of active interaction rather than simply being a projected association of unrelated galaxies at similar redshifts. The kinematic evidence from spectroscopic observations reinforces the morphological evidence. Multiple early universe systems identified in Webb data show velocity dispersions and velocity gradients inconsistent with undisturbed rotation and more consistent with the disordered, turbulent velocity fields that simulations predict during and after major mergers. Gas in merging systems is shocked and accelerated by the passage of the 2 galaxies through each other, producing broad emission line profiles that can be distinguished from the narrow, symmetric lines of undisturbed gas rotation. The fraction of high redshift galaxies in Webb spectroscopic surveys showing these disturbed kinematic signatures is higher than Lambda CDM predictions for the major merger rate at those epochs. Consistent with an elevated early universe merger rate. The environmental structure of the early universe contributes additional evidence for accelerated assembly. Webb's deep field surveys have identified multiple overdense galaxy structures, protoclusters and protogroups, at redshifts above 7, where the standard model predicts such structures to be rare and their galaxy populations to be modest in number and stellar mass. These early overdensities contain galaxies with systematically higher star formation rates and more disturbed morphologies than the surrounding field population, consistent with the environmental enhancement of galaxy growth and interaction that dense environments produce. The existence and properties of these early overdense structures imply that large-scale structure was assembling on timescales faster than Lambda CDM simulations reproduce, with the seeds of today's massive galaxy clusters already in place when the universe was less than 1 billion years old. The physical consequences of elevated early merger rates propagate throughout the galaxy formation process. Mergers drive gas toward the centers of the merging galaxies through tidal torques and gravitational disturbances, triggering centrally concentrated starbursts, brief but intense episodes of rapid star formation, and feeding central supermassive black holes that grow rapidly during these episodes. If mergers are more common in the very early universe than the standard model predicts, the starburst-driven stellar mass growth and the merger-driven black hole growth are both amplified above standard expectations, contributing to the excess massive galaxies and massive black holes that Webb has identified. The elevated merger rate is therefore not an isolated finding, but a potential physical mechanism linking multiple distinct Webb anomalies through a common dynamical process. The overcrowded early universe. The standard Lambda CDM model predicts not just the properties of individual early galaxies, but the spatial distribution of those galaxies, how they are clustered together in space, how frequently they occur in groups and overdense regions, and how the density of galaxy environments in the early universe compares to the density at later times. These clustering predictions follow from the same hierarchical structure formation framework that makes predictions about galaxy masses and morphologies, and they are testable in detail with Webb's wide-area deep field surveys that characterize the positions and redshifts of thousands of early galaxies simultaneously. The surprising finding from Webb's clustering measurements is that the early universe at redshifts above 6 is significantly more spatially structured than the standard model predicts. Rather than a relatively uniform distribution of proto-galactic fragments, Webb surveys reveal pronounced overdensities, regions with galaxy number densities 5 to 10 times higher than the surrounding field, at redshifts where such overdensities should be rare. These protoclusters, the progenitors of the massive galaxy clusters that define the large-scale structure of the present-day universe, appear earlier and in greater numbers than Lambda CDM simulations produce in their high redshift galaxy population. The physical significance of early protoclusters extends far beyond their statistical properties. In dense environments, galaxies interact more frequently. Gas is compressed to higher densities by the gravitational potential of the surrounding structure, and the star formation and black hole growth rates are enhanced relative to field galaxies at the same epoch. The enhanced star formation rates already inferred for high redshift galaxies in general are even more pronounced in the protocluster members that Webb has characterized, suggesting that the dense early universe environments are amplifying an already elevated star formation efficiency. The most massive early galaxies that Webb has found, the red monsters, the little red dots, the most luminous Lyman break galaxies, are preferentially found in or near protocluster overdensities rather than in the field, consistent with a scenario where environmental density drives the most rapid and extreme early galaxy growth. One of the most striking individual protocluster systems identified in Webb data is an overdensity at a redshift of approximately 7.9, corresponding to an age of the universe of roughly 680 million years, that contains at least 14 spectroscopically confirmed members within a projected volume roughly 3 megaparsecs across. For context, the local group, the galaxy group containing the Milky Way, Andromeda, and several dozen smaller galaxies, spans approximately 3 megaparsecs. The early universe protocluster therefore packs 14 massive galaxies into a volume comparable to the local group's total extent, at an epoch when the standard model predicts that regions of this size should contain perhaps 2 or 3 galaxies above the detection threshold. The total stellar mass in the protocluster members, summed across all confirmed galaxies, exceeds 1 trillion solar masses, comparable to the total stellar mass of the entire present-day Virgo galaxy cluster, which has had an additional 13 billion years to accumulate that mass through continued star formation and accretion. The origin of such massive early protoclusters within the Lambda CDM framework requires the existence of dark matter halos of proportionally extraordinary mass at those redshifts. Halos massive enough to gravitationally bind the galaxy group and to have accreted the gas that fueled the observed star formation. The halo mass function predicted by Lambda CDM at redshift 8 gives the number of halos above a given mass per unit volume of the universe, and the observed protocluster properties imply halo masses at the very extreme tail of this distribution, objects so rare that finding one within Webb's survey volume is statistically improbable under the standard prediction, let alone finding multiple such structures in independent survey fields. The theoretical response to the protocluster abundance problem has focused on the possibility that the bias between the galaxy distribution and the underlying dark matter distribution, the galaxy bias, is different in the early universe than at lower redshifts. If early galaxies form preferentially in the highest density peaks of the dark matter distribution with a higher bias than present-day galaxies, the observed galaxy overdensities could be more extreme than the underlying dark matter overdensities, potentially reconciling the observation with the standard halo abundance prediction. This is a plausible mechanism, and some simulations do predict higher galaxy bias at high redshift. But the quantitative reconciliation has not been demonstrated. The bias enhancement required to match the Webb protocluster observations is larger than current simulations naturally produce, adding another quantitative tension to the list that the standard model must address. Reionization and the cleared bubbles. The epoch of reionization, the transition of the intergalactic medium from a neutral state to the ionized state it maintains today, is one of the most important physical processes in cosmic history, and one that Webb is characterizing in unprecedented detail. Understanding reionization is not merely a matter of historical interest in the universe's evolution. It is a direct probe of what the first galaxies were doing, how efficiently they produced ionizing ultraviolet radiation, and how that radiation propagated through the neutral hydrogen that filled intergalactic space in the universe's first billion years. Following the cosmic microwave background emission at 380,000 years after the Big Bang, the universe entered the cosmic dark ages, a period during which the intergalactic medium was filled with neutral hydrogen. The first stars had not yet formed, and no sources of radiation existed to illuminate the cosmos. The Dark Ages ended when the first stars ignited, perhaps 100 to 200 million years after the Big Bang. These first stars produced intense ultraviolet radiation capable of ionizing the surrounding hydrogen, carving out expanding bubbles of ionized gas in the otherwise neutral medium. As more stars and galaxies formed, their ionizing radiation drove the bubbles to expand, and as the bubbles grew, they eventually began to merge. The merger of these ionized regions drove the global neutral hydrogen fraction down from essentially 1 towards 0, completing reionization by approximately 1 billion years after the Big Bang at a redshift of roughly 6. The standard model of reionization, built on pre-Webb observations, predicted a relatively gradual and smooth process. the ionized fraction of the intergalactic medium was expected to rise slowly from 0 at high redshift, cross 50% at roughly redshift 7, and reach 100% by redshift 6. The sources driving reionization in most pre-Webb models were the collective ultraviolet output of large numbers of faint low-mass galaxies. Not individually spectacular, but collectively sufficient to produce the required ionizing photon budget. Large, bright galaxies were expected to contribute, but not dominate. The process was supposed to be spatially relatively uniform. The bubble distribution should be smooth, without large regions that were ionized far ahead of their surroundings. Webb's observations are revealing a process that is both faster and more spatially inhomogeneous than this picture describes. The detection of Lyman alpha emission from galaxies at redshifts above 7 is the primary observational probe of the neutral fraction of the intergalactic medium at those epochs. Lyman alpha photons, produced when electrons in hydrogen atoms transition from the second to the first energy level after being ionized and recaptured, are resonantly scattered and absorbed by neutral hydrogen. In a neutral intergalactic medium, Lyman alpha photons, emitted by a high redshift galaxy, are absorbed before they can escape the local environment and reach a distant observer. Their detectability depends on the galaxy having cleared a sufficiently large ionized bubble around itself for the photons to escape the resonant scattering region before entering the bulk neutral medium. Webb has detected Lyman alpha emission from multiple galaxies at redshifts above 7 and 8, where the intergalactic medium was expected to be substantially neutral. The detection of these emissions implies that the emitting galaxies had already cleared ionized bubbles large enough to allow Lyman alpha escape, bubbles whose sizes, inferred from the observed Lyman alpha line profiles and escape fractions, are substantially larger than simple models of individual galaxy ionization predict. The most extreme case documented before 2025 was the galaxy JADES GSZ 13-1 at a redshift of approximately 13.4, corresponding to 330 million years after the Big Bang, which showed Lyman alpha emission at an epoch when essentially all models predicted the intergalactic medium to be almost entirely neutral. The detection implies an ionized region around this galaxy large enough to allow Lyman alpha photons to redshift out of resonance before encountering significant neutral hydrogen, a bubble radius of several megaparsecs, comparable in scale to the bubbles expected only much later in the reionization process. The physical explanation for these large early bubbles requires either that individual galaxies were producing ionizing photons far more efficiently than standard models assume, perhaps because the stellar populations of first galaxies were hotter, more massive, or less metal-rich than their later counterparts, increasing the ionizing photon production rate per unit stellar mass, or that the early galaxies found by Webb were not isolated, but were members of overdense groups or protoclusters whose combined ionizing output could maintain large bubbles against the recombination of the surrounding gas. Both explanations are physically motivated, and the protocluster detections by Webb in the same redshift range where the large Lyman alpha bubbles are found provide circumstantial support for the environmental explanation. The resolution likely involves both effects operating simultaneously. The broader implication is that reionization was not a smooth, gradual process driven by a uniform galaxy population. It was patchy, a mosaic of ionized regions growing around overdense galaxy concentrations, with large ionized bubbles forming early around the most overdense structures, while underdense voids remained neutral until much later. This inhomogeneous reionization topology is predicted qualitatively by some theoretical models, but is more pronounced in Webb's observations than those models describe. Its consequences extend to measurements of the 21 centimeter signal from neutral hydrogen at high redshifts, which upcoming radio telescopes, including the Square Kilometre Array, will use to map the three-dimensional ionization structure of the reionization epoch directly. Webb's characterization of the galaxy sources driving reionization provides the boundary conditions for interpreting those future observations. The Hubble tension. Among all the challenges facing modern cosmology, the Hubble tension occupies a unique position. It was known before Webb launched, has been measured with increasing precision for more than a decade, has resisted every proposed explanation within the Lambda CDM framework, and was expected by many in the community to be resolved by Webb's precision infrared observations. It was not resolved, it was confirmed. And its confirmation changes what the tension means, elevating it from a potential systematic measurement error to an established discrepancy that the standard model must account for. The Hubble tension is a disagreement between two independent classes of measurement of the Hubble constant, the parameter that describes the current rate at which the universe is expanding. The Hubble constant, denoted h0, is conventionally expressed in units of kilometers per second per megaparsec, where 1 megaparsec equals approximately 3.26 million light-years. A Hubble constant of 70 kilometers per second per megaparsec means that a galaxy 1 megaparsec away is receding at 70 kilometers per second due to the expansion of space. A galaxy 2 megaparsecs away is receding at 140 kilometers per second, and so on linearly with distance. The Hubble constant sets the absolute scale of all cosmological distance and time measurements, which is why its precise value matters so much to the rest of cosmology. The first class of measurement uses the cosmic distance ladder, a chain of overlapping distance measurement techniques that together extend from the nearest stars to the most distant observable supernovae. The foundation of the ladder is parallax, the geometric shift in the apparent position of a nearby star when viewed from opposite sides of Earth's orbit around the Sun, which gives a direct, assumption-free geometric distance to stars within a few thousand light-years. The second rung extends to distances of tens of millions of light-years using Cepheid variable stars, stars that pulsate in brightness, with a period precisely correlated with their intrinsic luminosity through the period-luminosity relation established by Henrietta Swan-Leavitt in the early 20th century. Measuring the apparent brightness of a Cepheid and knowing its intrinsic luminosity from its pulsation period gives the distance directly from the inverse square law. The third rung extends to hundreds of millions of light-years using Type Ia supernovae, thermonuclear explosions of white dwarf stars that reach a characteristic peak luminosity, making them useful as standardizable candles at cosmological distances where Cepheids cannot be individually resolved. The cosmic distance ladder measurements, led by the SH0ES collaboration using Hubble Space Telescope data, supplemented by Gaia satellite parallaxes for the nearest calibrator stars, converge on a Hubble constant of approximately 73 kilometers per second per megaparsec, with an uncertainty of roughly 2%. The second class of measurement uses the cosmic microwave background, analyzed within the Lambda CDM model, to infer the Hubble constant from the angular scale of the acoustic oscillation pattern imprinted on the CMB. The Planck satellite's final CMB analysis gives a Hubble constant of approximately 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. The difference between 73 and 67 kilometers per second per megaparsec is approximately 9%. The combined statistical significance of the discrepancy, accounting for the quoted uncertainties of both measurements, is approximately 5 sigma, the threshold conventionally used to claim a new discovery in particle physics, and far above the level at which the discrepancy could plausibly arise from random statistical fluctuation in otherwise correct measurements. At 5 sigma, the probability that the discrepancy arises purely from statistical fluctuation, that both measurements are correct, and the difference is a coincidence, is less than 1 in 3 million. This does not mean the measurements are wrong in the sense of being carelessly executed or incompetently analyzed. Both programs represent decades of careful work by large, technically sophisticated teams using state-of-the-art instruments and analysis methods. The SH0ES team has measured thousands of Cepheid variables in dozens of supernova host galaxies with meticulous attention to systematic error. The Planck team's CMB analysis is arguably the most thorough and carefully validated cosmological measurement ever performed. Both measurements are right, in the sense that they correctly measure what they claim to measure. The problem is that what they correctly measure does not agree. Something is wrong either with the physics that connects the measurements, the Lambda CDM model used to interpret the CMB, or with one of the measurement chains at a level subtle enough to have escaped detection despite years of scrutiny. Webb confirmed the tension is real. The most plausible systematic error in the distance ladder measurement was always the Cepheid rung. Cepheid distances are derived from apparent brightnesses measured at optical wavelengths where interstellar dust, both within the host galaxies and along the line of sight, can absorb and redden the Cepheid light, causing the distance to be overestimated. If the dust corrections applied to the SH0ES Cepheid photometry were systematically too small, if there was more dust than the optical reddening measurements indicated, perhaps because some of the dust was grey and produced attenuation without reddening, the corrected luminosities would be too faint and the inferred distances too large. Larger distances would imply a higher expansion rate, which would artificially inflate the derived Hubble constant. This systematic bias, if it existed, could in principle explain the tension as a measurement artifact rather than a physical discrepancy. Webb was designed to test this possibility definitively because its infrared sensitivity makes it far less vulnerable to the effects of interstellar dust than Hubble's optical photometry. Dust attenuation varies as an inverse power of wavelength. At 2 micrometers in the near-infrared, dust produces roughly 10 times less attenuation than at 0.5 micrometers in the visible. A Cepheid measured at near-infrared wavelengths is therefore far less affected by dust than the same Cepheid measured optically. If the dust correction was the source of the Cepheid-based Hubble constant being systematically too high, Webb's infrared Cepheid measurements, with their drastically reduced dust sensitivity, should give shorter distances and a lower Hubble constant, bringing the distance ladder value into agreement with the CMB-based value and resolving the tension. The SH0ES team conducted exactly this test using Webb. They re-observed the Cepheid populations in multiple supernova host galaxies with NIRCam at 1.5 micrometers and 4.4 micrometers. Wavelengths where dust attenuation is reduced by factors of approximately 8 and 25 relative to the Hubble optical photometry. The near-infrared Cepheid magnitudes were measured with the same precision and methodology as the original Hubble optical measurements, enabling a direct comparison. The results were unambiguous and were published in a 2023 paper by Rees and colleagues. The infrared Cepheid measurements gave distances consistent with the Hubble optical distances to within the measurement uncertainties. The dust correction in the SH0ES analysis was not systematically wrong. The Hubble constant derived from the infrared Cepheid distances was 73 km per second per megaparsec, identical within uncertainties to the value derived from the optical measurements. This result eliminates dust as the source of the Hubble tension. It does not prove that all other potential systematic errors in the distance ladder are negligible. The Cepheid period luminosity calibration, the metallicity dependence of the relation, the statistical treatment of the supernova standardization, and other factors remain as possible contributors. But it removes the most physically motivated and most widely discussed candidate systematic. Independent distance ladder measurements using methods that do not depend on Cepheids at all. The tip of the red giant branch method, which uses a physically different population of stars as the second rung calibrator, give Hubble constants in the range of 69 to 72 km per second per megaparsec, intermediate between the Cepheid-based and CMB-based values, but still above the CMB prediction, and consistent with a real discrepancy, rather than a Cepheid-specific artifact. The confirmation that the Hubble tension survives the most powerful systematic test that could be applied to it transforms the tension from a potential measurement error into an established astrophysical fact. The universe is expanding faster today than the Lambda CDM model, calibrated against the early universe as measured by Planck, predicts it should be. This statement is now as well established observationally as any quantitative claim in modern cosmology. The question is no longer whether the tension is real. The question is what physics is responsible for it. The cosmic microwave background meets Webb. The cosmic microwave background is the oldest observable light in the universe. It was emitted 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen for the first time. And the photons that had been trapped in the hot plasma were suddenly free to travel unimpeded in all directions. For 13.8 billion years, those photons have been traveling through the expanding cosmos, stretching from their original wavelengths in the infrared and visible into the microwave band, where they are detected today as a nearly uniform glow filling the entire sky. The Planck satellite's final measurement of the cosmic microwave background, released in 2018, characterized its temperature fluctuations with a precision of better than 1 part in 10 million. And the Lambda CDM model reproduces those fluctuations with 6 free parameters to within measurement uncertainties across the full range of angular scales, from the whole sky down to fractions of a degree. What the cosmic microwave background measurement establishes is the initial conditions of the universe at 380,000 years, the specific pattern of density fluctuations that would grow under gravity into the large-scale structure of galaxies and galaxy clusters observed today. These initial conditions are not merely a starting point for simulations. They are a tight constraint on the total energy budget of the universe, the density of ordinary matter, the density of dark matter, the spatial curvature of the universe, the amplitude and slope of the primordial density fluctuation spectrum, and the Hubble constant at the epoch of recombination. The Planck measurement constrains all 6 of these parameters simultaneously, and the constraints are extraordinarily tight. The density of ordinary baryonic matter, for example, is constrained to within approximately 1% of its measured value. The connection between Webb and the cosmic microwave background operates on 2 levels. At the direct level, Webb's observations of the earliest galaxies are probing the epoch immediately following the cosmic microwave background emission, the first few 100 million years, during which the density fluctuations seen in the CMB began to grow into the first gravitationally collapsed structures. Webb is therefore the observational bridge between the initial conditions established at recombination and the galaxy properties measured at later times, and inconsistencies between what the CMB predicts for early structure formation and what Webb observes in early galaxies are a direct signal of missing physics in the theoretical framework connecting the 2 epochs. At the indirect level, the Hubble constant derived from the CMB by the Planck analysis, 67 km per second per megaparsec, is one of the 2 conflicting values at the center of the Hubble tension that Webb's Cepheid measurements have confirmed. The Planck value is derived not from any direct measurement of the expansion rate, but from fitting the Lambda CDM model to the CMB power spectrum and using the best fit model to predict what the Hubble constant should be today. The prediction is only as good as the model. If the Lambda CDM model correctly describes the physics of the universe between the CMB epoch and today, if the energy content, the dark matter properties, and the expansion history are all correctly captured by the standard framework, then the CMB-derived Hubble constant should match the directly measured local value. It does not. The discrepancy is the Hubble tension, and it implies that the Lambda CDM model is missing something in its description of the intervening 13.8 billion years. The specific implication is profound. The cosmic microwave background is telling us about the universe at recombination, and the local distance measurements are telling us about the universe today. And the model that is supposed to connect the 2 is getting the answer wrong by 9%. This is not a data problem. Both datasets are extraordinarily precise. It is a theory problem. The bridge between the oldest observable light in the universe and the present-day expansion rate is broken in some way that the standard model does not describe, and understanding what is broken requires either new physics in the dark energy sector, new physics in the dark matter sector, new physics in the neutrino sector, or some combination of extensions that together reproduce the full suite of cosmological observations while resolving the specific discrepancy between the early universe calibrated and locally measured expansion rates. No such combination has yet been identified and accepted by the community. Webb's role in this specific puzzle is as a precision instrument for one of the chains in the local distance measurement, the infrared Cepheid program that tested and confirmed the SH0ES result. But its broader role is as the observational probe of the epoch that connects the CMB to the present, and every anomaly it finds in the properties of early galaxies is simultaneously a constraint on the physics of that bridge. The excess of massive early galaxies implies either that the initial conditions at recombination produced more large-scale density fluctuations than the CMB power spectrum indicates, or that the growth of those fluctuations into halos and galaxies was faster than the standard matter-dominated growth rate predicts, or that the star formation efficiency within early halos was systematically higher than current models assume. Each of these possibilities has specific implications for the CMB to present connection and therefore for the Hubble tension. The anomalies are not independent. They are facets of the same underlying incompleteness in the Lambda CDM framework. The future of this connection is in the hands of next-generation CMB experiments, particularly the Simons Observatory and CMBS-4, ground-based arrays that will measure the CMB polarization pattern and small-scale temperature fluctuations with sensitivity far exceeding Planck. These experiments will constrain the sum of neutrino masses, the number of relativistic species in the early universe, and the amplitude of primordial gravitational waves with a precision that will rule in or out many of the proposed Hubble tension resolutions. Combined with Webb's characterization of early galaxy formation and the deci-baryon acoustic oscillation measurements of the expansion history at intermediate redshifts, the full dataset available to cosmologists in the next decade will either identify the resolution to the Hubble tension or establish that it requires a fundamental revision of the cosmological framework at a level not yet contemplated in the theoretical literature. What the tension actually implies. The Hubble tension, confirmed as a real discrepancy between the early universe calibrated expansion rate and the directly measured local expansion rate, implies that something is wrong with our description of the universe's expansion history between the epoch of the cosmic microwave background emission and the present day. Within the Lambda CDM framework, the expansion history is completely determined by the energy content of the universe, the densities of ordinary matter, dark matter, and dark energy, and by the initial conditions established by inflation. If the CMB correctly measures the expansion rate at 380,000 years after the Big Bang, and if the local measurements correctly measure the expansion rate today, and if they disagree at the level of 9%, then something happened between then and now that the Lambda CDM model does not describe. The theoretical landscape of proposed explanations is broad and has been extensively explored since the tension became statistically compelling around 2019. The proposals fall into several broad categories, each with different physical content and different observational tests. The first category involves modifications to the dark energy sector, proposals that dark energy is not a cosmological constant but a dynamical field whose energy density evolves with cosmic time in a way that produces more expansion than the cosmological constant predicts. If dark energy was more energetically dense in the past than its current value implies, the expansion rate at intermediate redshifts would have been boosted, producing a higher inferred Hubble constant when extrapolating from the CMB epoch to the present. The challenge for these models is that the expansion history is constrained not just by the Hubble constant measurements, but by the entire distance redshift relation measured using baryon acoustic oscillations and supernovae at intermediate redshifts, and models that resolve the Hubble tension often introduce discrepancies at these intermediate scales. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first year of baryon acoustic oscillation measurements using over 6 million galaxy spectra, and the results suggested that dark energy may not be a cosmological constant. The DESI data showed tentative evidence, at the 2 to 3 sigma level, for an evolving dark energy equation of state, consistent with the value of the dark energy density being different in the past than today. This finding is not yet confirmed and requires additional data from DESI's ongoing 5-year survey before it can be treated as established. But it is the first direct observational hint, independent of the Hubble tension, that the cosmological constant description of dark energy may be incomplete. If confirmed, it would represent the second major challenge to Lambda CDM beyond the galaxy formation anomalies that Webb is revealing. A challenge rooted not in the physics of galaxy formation, but in the fundamental physics of the universe's acceleration. The second category of Hubble tension resolution involves modifications to the physics of the early universe, specifically to the conditions just before the epoch of the CMB emission. One of the most discussed proposals is the early dark energy model, which posits a new form of dark energy that was present in the early universe and then effectively disappeared by redshift of roughly 3000, leaving no trace in the present-day expansion. Early dark energy would have boosted the expansion rate slightly during the pre-recombination epoch, reducing the acoustic horizon scale imprinted on the CMB and shifting the inferred Hubble constant upward. The model can resolve the Hubble tension if the early dark energy contribution is tuned to the right amplitude, but it generally introduces tensions with other cosmological datasets, particularly the clustering of galaxies at low redshift, that require additional modifications to resolve. The honest assessment is that no proposed resolution to the Hubble tension has achieved broad acceptance in the cosmological community. Every model that resolves the tension does so by introducing new physics that produces observable consequences elsewhere, and those consequences are generally in tension with other well-established measurements. This suggests either that the correct resolution has not yet been identified, that multiple extensions to the standard model are simultaneously required, or that the resolution involves physics so different from anything currently proposed that the field has not yet conceived of it. The Hubble tension may be the most important unsolved problem in quantitative cosmology, and Webb's confirmation that it is real rather than resolving it has deepened its significance. Star formation was faster and more violent. One of the most consistent quantitative findings across Webb's entire program of early universe observations is that star formation in the early universe was not merely more rapid than the standard model predicted. It was more efficient, more concentrated, and apparently proceeded under physical conditions that current simulations do not reproduce. The discrepancy is not confined to the most massive, most anomalous systems like the red monsters. It appears across the full stellar mass range of early galaxies, in the specific star formation rates, the star formation efficiency per unit gas mass, the compactness of star-forming regions, and the physical properties of the ionized gas that traces the most recently formed stellar populations. The specific star formation rate, the star formation rate per unit of existing stellar mass, evolves systematically with redshift in the Lambda CDM framework, driven by the increasing availability of cold gas at earlier cosmic times. This evolution is well constrained at redshifts below 4 from Hubble and ground-based observations, and the models reproduce it reasonably well in that regime. At redshifts above 4, the model predictions extrapolate from the well-constrained lower redshift behavior under the assumption that the same physical processes, gas cooling, star formation, stellar feedback, operate in the same way at earlier times. Webb's measurements at redshifts above 6 show specific star formation rates systematically elevated above these extrapolations by factors of 2 to 5 across the full range of galaxy stellar masses sampled. the elevation is not dominated by the most extreme outliers. It is the systematic trend across the typical galaxy population that represents the most significant finding. The compactness of star-forming regions in early galaxies is a related and independent finding. In the present-day universe, star formation is distributed across molecular clouds spread throughout a galaxy's disk, with individual star-forming complexes spanning tens to hundreds of light-years, and the total star-forming disk extending over tens of thousands of light-years. In early galaxies at high redshift, Webb's imaging reveals that a substantial fraction of the total star formation is concentrated in extremely compact regions, sometimes a single central concentration smaller than 1 kiloparsec in effective radius. This compactness implies extremely high star formation rate surface densities, star formation rates per unit area, far exceeding the most intense star-forming regions in present-day galaxies. The physical conditions that produce this compactness are not well understood. In present-day galaxies, star formation rate surface density is limited by stellar feedback. The radiation pressure and mechanical energy input from young massive stars that drive gas out of star-forming regions and limit how densely star formation can proceed. At the extreme surface densities implied by early compact galaxies, this feedback should be even more intense, making the maintenance of such densities difficult to explain within current models. The theoretical response has generally involved proposing that early galaxies had higher gas fractions than present-day galaxies, more gas relative to stellar mass, and that this higher gas fraction enabled the maintenance of high star-forming densities by continuously replenishing the gas expelled by stellar feedback. This is physically motivated, but has not been confirmed by direct gas mass measurements in early galaxies, which remain technically challenging. Webb's spectroscopy of the ionized gas in early star-forming galaxies has revealed physical conditions distinct from those in lower redshift star-forming galaxies in ways that may help explain the enhanced star formation rates. The emission line ratios from ionized gas, particularly the ratios of oxygen, nitrogen, and hydrogen lines that together encode the ionization parameter and the electron density, indicate that the interstellar gas in early galaxies has higher ionization parameters and higher electron densities than gas in present-day star-forming galaxies at the same metallicity. The higher ionization parameter reflects more intense radiation per unit gas mass, consistent with a stellar population that is younger, more massive, and producing more ionizing photons per solar mass than typical present-day stellar populations. The higher electron density reflects a more compact, pressurized interstellar medium. Together, these properties paint a picture of early galaxies as physically extreme environments, denser, hotter, more radiation intense, where the star formation process operates under conditions with no close present-day analog. The mature galaxies that stopped forming stars too early. Among all the populations of anomalous early universe objects identified by Webb, one has received less public attention than the red monsters or little red dots, but carries some of the most profound implications for galaxy formation physics. This population consists of massive galaxies at redshifts between 3 and 6, seen when the universe was between 1 and 2 billion years old, that have already stopped forming stars. They are massive. They are red from old stellar populations rather than from dust, and they are quiescent. Their star formation rates are essentially zero, placing them in the same physical category as the dead elliptical galaxies that populate the centers of present-day galaxy clusters. The problem is that they should not be dead yet. In the Lambda CDM framework, the quenching of star formation in massive galaxies, the transition from active star-forming disk galaxies to passive red elliptical systems, is driven primarily by feedback from the central supermassive black hole in its active accretion phase. When the black hole accretes gas at high rates, it releases enormous amounts of energy through jets and radiation that heat the surrounding gas, expel it from the galaxy, and cut off the fuel supply for further star formation. This feedback mechanism is called active galactic nucleus quenching, and it is the dominant quenching process in most current galaxy formation models for massive systems. The process takes time. The black hole must grow to sufficient mass. Its energy output must couple efficiently to the surrounding gas, and the gas must be expelled or heated on a timescale comparable to the orbital period of the galaxy. In present-day models, this sequence typically requires at least several 100 million years and often longer. Massive quiescent galaxies at redshifts above 3 therefore imply that the entire sequence of star formation, black hole growth, and active galactic nucleus quenching completed within the first billion to 2 billion years of cosmic history. This is already compressed relative to model predictions. What makes the Webb-identified early quiescent population particularly challenging is the combination of their stellar masses, tens of billions of solar masses, again approaching or exceeding the Milky Way, with the stellar population ages inferred from spectroscopy. Webb's NIRSpec spectra of early quiescent galaxies show the characteristic spectral features of old stellar populations. Strong Balmer absorption lines from intermediate mass stars, the D4000 spectral break produced by metal line absorption in the atmospheres of cool stars. And the modeling of these features gives stellar population ages, suggesting that the stars in these galaxies formed and the star formation subsequently quenched within the first 500 million to 700 million years after the Big Bang. The timing is extraordinarily constrained. A galaxy with a stellar mass of 50 billion solar masses, whose stars formed in a burst lasting perhaps 200 million years, and which has then been passively evolving for a further 400 million years to reach its observed epoch, requires a star formation rate during the burst of roughly 250 solar masses per year, already above the rate sustainable by the most vigorously star-forming present-day galaxies over extended periods. The subsequent quenching must have been complete, not merely reduced, but effectively zero, for the passive evolution inferred from the stellar population age to be consistent with the spectral observations. Complete quenching in the early universe, before the black hole feedback mechanisms have had adequate time to operate, points either to a qualitatively different quenching mechanism than the standard active galactic nucleus feedback model describes, or to active galactic nucleus feedback operating on much shorter timescales in the early universe than in present-day analogues. One proposed mechanism for rapid early quenching involves the exhaustion of the gas supply by the extreme star formation rates themselves, without requiring active galactic nucleus feedback at all. If a galaxy converts gas to stars with sufficient efficiency over a short enough interval, it can simply use up all the available gas before any quenching mechanism has time to act. This stellar exhaustion scenario requires star formation efficiencies substantially higher than present-day values. Essentially, all the available gas must be converted to stars rather than the few percent per freefall time that current observations imply. But it avoids the timing problem of active galactic nucleus feedback. Webb's characterization of gas fractions in early quiescent galaxies, which requires indirect inference from the spectral energy distribution in the absence of direct molecular gas emission line measurements, is consistent with extremely gas-poor systems, supporting the exhaustion scenario, but not conclusively distinguishing it from feedback-driven quenching. Future observations with the Square Kilometre Array that directly detect or set upper limits on molecular gas in early quiescent systems will provide the discriminating test. The first black holes should not exist yet. The discovery that supermassive black holes of enormous mass exist in the early universe is not new to Webb. Pre-Webb quasar surveys had already identified supermassive black holes exceeding 1 billion solar masses at redshifts above 6, establishing that such objects existed when the universe was less than 1 billion years old. But Webb has dramatically changed the picture by revealing that massive black holes are not just present, but abundant at these early epochs, and that their properties, their masses, their host-galaxy relationships, their accretion states, differ systematically from what both pre-Webb observations and theoretical models predicted. The fundamental theoretical problem with early massive black holes is one of growth time. In the Standard Model, the first black holes form as remnants of the first massive stars, population 3 stars, when those stars exhaust their nuclear fuel and collapse. The expected mass of a stellar remnant black hole from a very massive first-generation star is on the order of tens to hundreds of solar masses, depending on the mass of the progenitor star and the dynamics of the collapse. Growing from a seed of 100 solar masses to 1 billion solar masses, the mass of some of the quasar black holes identified before Webb, requires a factor of 10 million in mass increase. At the theoretical maximum accretion rate set by the Eddington limit, the E-folding time for black hole mass growth is approximately 45 million years. To grow by a factor of 10 million requires roughly 16 E-folding times, or about 720 million years of continuous Eddington rate accretion. For a black hole at 1 billion solar masses to be in place at a redshift of 6, corresponding to 900 million years after the Big Bang, it had to start growing from its stellar mass seed, essentially immediately after the Big Bang, and maintain maximum accretion continuously for the entire intervening period without any interruptions. This constraint was already known before Webb. What Webb has added is the discovery that massive black holes are not confined to the exceptional, individually luminous quasars that pre-Webb surveys could identify. The little red dot population, if many of its members harbor accreting black holes as the spectroscopic evidence suggests, implies a far larger population of massive black holes at high redshift than was inferred from quasar counts alone. The number density of black holes implied by the little red dot population at redshifts between 4 and 7 is 10 to 100 times the number density of conventional quasars at the same epoch. If even a fraction of the little red dots harbor black holes of 100 million to 1 billion solar masses, the total mass in supermassive black holes in the early universe is vastly larger than any prior estimate. This population excess requires a rethink not just of black hole growth rates, but of black hole formation. The stellar remnant seeds of population 3 stars growing at Eddington rates cannot produce enough mass in enough black holes to match what Webb is finding. Two alternative seeding mechanisms have attracted theoretical attention. The first is the formation of intermediate mass black hole seeds through the collapse of dense stellar clusters, regions where the stellar density is so high that stars merge and collapse into a single massive object with a mass of perhaps 10,000 to 100,000 solar masses. The second and more radical possibility is direct collapse black holes, the gravitational collapse of massive metal-free gas clouds directly into black holes of 100,000 to 1 million solar masses, bypassing the conventional stellar evolution phase entirely. Direct collapse requires specific conditions: a strong ultraviolet background that prevents the gas from cooling and fragmenting into stars, combined with a massive enough gas cloud to overcome any remaining pressure support. But if those conditions were met frequently in the early universe, the resulting massive seeds could grow more easily to the observed masses within the available time. Webb's spectroscopic characterization of little red dots and other early active galactic nucleus candidates is providing constraints on the black hole masses and accretion rates that will distinguish between these seeding scenarios, but the data are not yet sufficient to identify which mechanism dominates. What is clear is that neither the stellar remnant seeding model nor the standard Eddington limited growth scenario can reproduce the observed population without modification, and that the modification required is substantial enough to represent genuinely new physics in the theory of black hole formation and growth. Dark matter's role is being questioned. The Lambda CDM model's predictions for galaxy formation depend critically on assumptions about the properties of dark matter. Specifically, that dark matter is cold, meaning that its thermal velocities in the early universe were negligible compared to the speed of light, and that it interacts with ordinary matter only through gravity. These assumptions produce specific predictions for the abundance and internal structure of dark matter halos that form the scaffolding for galaxies, and it is these predictions that galaxy formation observations test. Webb's anomalous findings about the early galaxy population have renewed scrutiny of whether the standard cold dark matter model correctly describes the small-scale structure of the universe. The most persistent tension between cold dark matter predictions and observations at small scales is the cusp core problem. Numerical simulations of cold dark matter halo formation consistently predict that the dark matter density in the central regions of halos should rise steeply toward the center, a cusp, with the density profile described by the Navarro-Frenk-White functional form. Observations of the rotation curves of dwarf galaxies. Measurements of how fast gas and stars orbit at different distances from the galaxy center, which directly probe the gravitational potential and therefore the mass distribution, including dark matter, often show flat, constant density cores, rather than the predicted steep cusps. This core cusp tension has been debated for decades, with proposals ranging from baryonic feedback processes that rearrange the dark matter distribution through repeated bursts of star formation, to modifications to the dark matter physics itself, such as self-interactions or warmth that would naturally produce chord profiles. Webb's characterization of the internal structure of early dwarf galaxies at high redshift adds new data to this debate. Kinematic measurements from NIRSpec of dwarf mass galaxies at redshifts above 4 provide constraints on the dark matter density profiles of small halos in the early universe, before the baryonic feedback that could potentially reshape them has had as long to operate. The early results suggest that the core cusp tension may be present even in the young universe, which would disfavor the baryonic feedback explanation and strengthen the case for modified dark matter physics. These measurements are still preliminary and carry substantial uncertainties, but they represent the first attempts to probe dark matter halo structure at small scales in the early universe, a regime where the competing models make different predictions. The abundance of satellite galaxies is a related tension that Webb is beginning to address. Cold dark matter simulations predict that massive galaxies like the Milky Way should be surrounded by thousands of dark matter subhalos, each potentially hosting a faint satellite galaxy. The observed number of satellite galaxies around the Milky Way and Andromeda is much smaller than this prediction, the missing satellites problem, though some of the discrepancy may reflect the difficulty of detecting the faintest satellites rather than their genuine absence. Webb's deep imaging is providing much more sensitive searches for faint satellite galaxies around nearby galaxies than were previously possible, and the results will provide new constraints on whether the predicted abundance of dark matter substructure is actually present in the form of observable but previously undetected faint galaxies. The most radical possibility raised by Webb's early universe findings is that the initial conditions of structure formation, the spectrum of primordial density fluctuations that seed all subsequent structure, are different from what the Lambda CDM model assumes. Modifications to the primordial power spectrum, primordial black holes as a component of dark matter, or alternative dark matter models with small-scale suppression of structure could in principle produce a galaxy population at high redshift more consistent with Webb's observations than standard cold dark matter predicts. These proposals are constrained by the extraordinary success of Lambda CDM in reproducing the large-scale structure and the cosmic microwave background, which limits any deviation from the standard initial conditions to be small in amplitude and confined to specific scales. Whether such modifications can resolve the Webb anomalies while remaining consistent with all other constraints is an active area of theoretical investigation. The chemical complexity of early galaxies. One of the most scientifically rich aspects of Webb's early universe observations is the chemical characterization of high redshift galaxies through spectroscopy. the measurement of the abundances of specific elements in the gas and stars of galaxies seen in the universe's first few billion years. These chemical measurements carry information about the star formation history, the initial mass function of stars, the efficiency of stellar feedback in expelling enriched gas from galaxies, and the degree of mixing and recycling of material between different galactic components. Before Webb, such measurements were available only for galaxies at modest redshifts, typically below 3, because the relevant emission lines were redshifted to wavelengths inaccessible to optical spectrographs on ground-based telescopes. Webb's infrared spectroscopy brings these measurements within reach for galaxies at redshifts up to 8 and beyond. The primary chemical diagnostic in emission line spectroscopy is the oxygen abundance, the ratio of oxygen to hydrogen in the ionized gas of star-forming regions, measured from the ratios of specific forbidden emission lines of doubly ionized and singly ionized oxygen relative to hydrogen recombination lines. Oxygen is the most abundant heavy element produced by stellar nucleosynthesis and the dominant coolant in the interstellar medium of star-forming galaxies, making its abundance the conventional proxy for overall gas phase metallicity. The relationship between galaxy stellar mass and gas phase metallicity, the mass-metallicity relation, is one of the most fundamental empirical relationships in galaxy evolution, reflecting the competition between the production of metals by star formation and their dilution by the inflow of metal-poor gas from the intergalactic medium, and their expulsion by supernova-driven outflows. Webb's mass-metallicity relation measurements at high redshift reveal that early galaxies were chemically less enriched at a given stellar mass than their low redshift counterparts, expected qualitatively since they have had less time for star formation to enrich their gas, but that the degree of enrichment is higher than some models predict, and that the scatter in the relation is larger. Some early massive galaxies show oxygen abundances approaching those of present-day galaxies at the same mass, implying rapid chemical enrichment through intense star formation and efficient retention of the produced metals. Others show very low metallicities, even at substantial stellar masses, consistent with significant dilution by metal-poor gas accretion. The bimodality in early galaxy chemical enrichment histories implied by this scatter is not well reproduced in Lambda CDM simulations, which tend to predict a tighter mass-metallicity relation at all redshifts. The nitrogen-to-oxygen ratio provides a complementary chemical probe that is sensitive to the enrichment by asymptotic giant branch stars, lower mass stars that produce nitrogen in their evolved phases, relative to the enrichment by core collapse supernovae that produce primarily oxygen and alpha elements. Several early galaxies observed by Webb show elevated nitrogen-to-oxygen ratios, inconsistent with simple models of chemical enrichment from a normal stellar initial mass function. One particularly striking example, GNZ11 at a redshift of approximately 10.6, showed nitrogen emissions so strong that its nitrogen-to-oxygen ratio implied a stellar population dominated by very massive stars producing nitrogen at rates far exceeding normal galaxy stellar populations. One interpretation involves Wolf-Rayet stars, very massive, evolved stars in brief phases of intense mass loss, contributing disproportionately to the nitrogen enrichment. Another involves the contribution of a supermassive star or dense stellar cluster with an unusual initial mass function. Neither interpretation is definitive, but the observation represents a clear chemical anomaly that standard models do not predict. The detection of carbon, silicon, and iron features in the spectra of some early galaxies through both emission and absorption spectroscopy adds further dimensions to the chemical picture. Carbon and silicon are produced in stellar nucleosynthesis on different timescales and through different channels than oxygen, and their ratios relative to oxygen encode information about the star formation timescale. Rapid star formation produces alpha element enhancement as core collapse supernovae dominate the enrichment before the delayed type Ia supernovae that produce iron have time to contribute. The alpha enhancement observed in some early massive galaxies is consistent with rapid, intense star formation histories, providing independent chemical confirmation of the dynamical evidence for high, early star formation rates. The chemical complexity of early galaxies, now accessible for the first time through Webb's infrared spectroscopy, is proving to be an extraordinarily rich diagnostic of their formation histories and of the physical conditions under which the first generations of stars formed and evolved. The observable universe's edge. The James Webb Space Telescope is capable of observing objects at look-back times of up to 13.6 billion years. Seeing the universe as it was when the cosmos was only about 200 to 300 million years old. But there is a boundary beyond which no telescope, no matter how capable, can ever see. And understanding that boundary is essential for understanding what Webb's observations mean in their full cosmological context. That boundary is the edge of the observable universe, not the edge of the universe itself, which may be infinite, but the edge of the region from which light has had time to reach us since the Big Bang. The observable universe has a radius of approximately 46.5 billion light-years. This number is larger than the age of the universe times the speed of light, 13.8 billion light-years, because the universe has been expanding throughout the time the light has been traveling. The most distant objects we can observe are not 13.8 billion light-years away. They are approximately 46.5 billion light-years away, because the space between us and those objects has expanded substantially since the light we are now receiving from them was emitted. An object that emitted light 13.8 billion years ago, when the universe first became transparent at recombination, is now approximately 46 billion light-years away because of the expansion that has occurred since then. The observable universe is therefore a sphere of 46.5 billion light-year radius centered on the Earth. Not because Earth is special, but because the observable universe is always centered on the observer. Beyond this sphere, objects exist. The universe is almost certainly much larger than the observable portion, possibly infinite, but their light has not had time to reach us since the Big Bang. No observation with any conceivable telescope can access information from beyond this boundary. It is a fundamental limit imposed by the finite age of the universe and the finite speed of light, not an engineering limitation that future technology can overcome. The light from objects beyond the observable horizon is on its way toward us, but has not yet arrived. We are, in a very real physical sense, unable to know what lies beyond this boundary, except through theoretical inference. Webb's observations push toward the inner edge of this boundary, not the recombination surface at 46.5 billion light-years, which emitted the cosmic microwave background and which every microwave telescope can observe, but the epoch of first galaxy formation at look-back times of 13.4 to 13.6 billion years, corresponding to co-moving distances of roughly 43 to 44 billion light-years. The most distant confirmed galaxy, JWST 14-0, at a redshift of 14.32, is seen at a look-back time of 13.63 billion years, a cosmic time of only 290 million years after the Big Bang. The light from this galaxy has been traveling for 13.63 billion years. The galaxy itself is now approximately 43 billion light-years away. We are seeing it not as it is now, but as it was when the universe was only 2% of its current age. What this means practically is that Webb is accessing a regime of cosmic history where the theoretical predictions of galaxy formation models are extrapolated far beyond the observational constraints that calibrated them. The models were built and tested against observations at redshifts below 4, where the bulk of the pre-Webb galaxy census existed. The Lambda CDM framework's predictions at redshifts above 6 are extrapolations of uncertain reliability, and it is these extrapolations that Webb is now testing and finding wanting. The boundary of the observable universe does not limit Webb's ability to see these early galaxies, but it does mean that what Webb finds there is genuinely new information about physical conditions that no prior observation had characterized, and that the surprise of the findings reflects the limits of the theoretical framework rather than the limits of the instrument. Lambda CDM is incomplete, not wrong. The cumulative weight of Webb's anomalous findings, the excess massive early galaxies, the red monsters, the little red dots, the early organized disk morphologies, the elevated star formation rates, the massive early black holes, the rapid chemical enrichment, might suggest that the standard model of cosmology has been falsified and that an entirely new framework is needed. This conclusion would be premature, and the distinction between the standard model being incomplete and it being wrong is not semantic. It has specific and important scientific implications for how the community should respond to the Webb findings. The evidence that the Lambda CDM framework is correct at the level of its foundational physical content is overwhelming and has not been weakened by any of Webb's observations. The Big Bang nucleosynthesis, predictions for the primordial abundances of hydrogen, helium, and deuterium are confirmed to within measurement uncertainties by observations of metal-poor stars and intergalactic gas. The cosmic microwave background temperature fluctuation pattern is reproduced by the Lambda CDM model with 6 parameters to the precision of the best measurements ever made. The large-scale distribution of galaxies, the baryon acoustic oscillation scale, the matter power spectrum on scales of tens to hundreds of megaparsecs, is correctly predicted by the model with the same 6 parameters. The existence and properties of dark matter, inferred from galaxy rotation curves, gravitational lensing, and large-scale structure, are consistent with the cold dark matter hypothesis. These are not minor successes. They are the foundational observational pillars of modern cosmology, and no alternative framework proposed to date reproduces all of them with comparable success. What Webb's observations demonstrate is that the specific implementation of galaxy formation physics within the Lambda CDM framework, the modeling of how gas cools, how efficiently it forms stars, how stellar feedback regulates star formation, how supermassive black holes form and grow, is inadequate for the early universe. This implementation is not a fundamental part of the Lambda CDM framework in the same way that the cosmological constant and cold dark matter are. It is a set of physical processes that must be incorporated into the framework as subgrid prescriptions in numerical simulations, and those prescriptions have been calibrated against observations at lower redshifts where Webb quality data did not previously exist. The appropriate response to Webb's findings is to revise these prescriptions, to identify what physical processes the models are missing or misrepresenting, rather than to abandon the underlying cosmological framework. The analogy to classical mechanics and quantum mechanics is instructive. Classical mechanics is not wrong in the sense of being inconsistent with observations at the scales where it was validated: planetary orbits, engineering structures, fluid dynamics. It is incomplete in that it fails to describe phenomena at atomic scales where quantum effects dominate. The appropriate response to this incompleteness was not to abandon classical mechanics, but to develop quantum mechanics as an extension that correctly describes the new regime while reproducing classical behavior in the appropriate limit. Similarly, Lambda CDM is not wrong at the scales and epochs where it has been tested. It is incomplete in its description of galaxy formation physics in the early universe at the level of detail that Webb can now probe. The appropriate response is theoretical development, new physics of star formation, stellar feedback, black hole seeding and growth, that extends the framework to correctly describe the new regime while remaining consistent with everything the framework already reproduces correctly. This theoretical development is underway. Multiple groups are revising their simulations to incorporate higher star formation efficiencies in the early universe, different feedback prescriptions, alternative black hole seeding mechanisms, and modified treatments of gas cooling and accretion. No single revision has yet produced a model that resolves all of the Webb anomalies simultaneously. But the direction of the required revisions is becoming clearer as the observational constraints accumulate. Webb is not breaking cosmology. It is revealing the frontier where the current theory must be extended, and it is providing the data needed to guide that extension. The simulation crisis. The discoveries from Webb's first 2 years have created what is being described in the theoretical astrophysics community as a simulation crisis. A situation in which the most sophisticated computational models of galaxy formation and cosmological structure available before the telescope's launch have been shown to be systematically incorrect in their predictions for the early universe, and where the corrections required to bring the models into agreement with observations are large enough to represent not incremental refinements, but qualitative changes in the physical prescriptions implemented in the simulations. Cosmological simulations of galaxy formation are among the most computationally demanding scientific calculations ever undertaken. The flagship simulations of the pre-Webb era, JWST, Eagle, Simba, and their successors, model volumes of the universe hundreds of megaparsecs across, tracking the gravitational evolution of dark matter, the hydrodynamics of gas, the formation and evolution of stars, the growth of supermassive black holes, and the feedback processes coupling these components across cosmic time. They run on some of the world's largest supercomputers for months, and their results have been calibrated against the observed properties of present-day galaxies, the mass function, the size-mass relation, the star formation main sequence, the color bimodality, with impressive success. The agreement between these simulations and the observations they were calibrated against was taken as evidence that the physical prescriptions implemented in the models were approximately correct. The problem is that calibration against present-day observations does not guarantee correct predictions for the early universe, because the physical conditions in the early universe, higher gas densities, lower metallicities, more frequent mergers, more intense radiation fields, are sufficiently different from the present-day conditions that the calibrated prescriptions may not apply. This extrapolation failure is precisely what Webb's observations are revealing. The illustrious TNG prediction for the stellar mass density at redshift 8 is a factor of 40 below the Webb measurement. The Eagle simulation produces essentially no galaxies with stellar masses above 10 billion solar masses at redshifts above 9. The Simba simulation, which implements a particularly aggressive active galactic nucleus feedback prescription designed to produce the observed quiescent galaxy population at low redshifts, quenches star formation in high redshift galaxies so efficiently that it underpredicts the observed luminosity function at redshift 6 by an order of magnitude. Every major simulation of the pre-Webb era fails to reproduce the Webb early galaxy population. And the failures are not in the same direction or of the same character, indicating that the problem is not a single missing ingredient, but a complex of physical processes that are all being modeled incorrectly in the early universe regime. The theoretical community's response to the simulation crisis has involved both targeted revisions of specific physical prescriptions and more fundamental rethinking of which physics dominates in the early universe. The targeted revisions have focused primarily on the stellar feedback prescription, the modeling of how supernova explosions and radiation from massive stars couple to the surrounding gas and limit star formation efficiency. In present-day galaxy simulations, stellar feedback is calibrated to produce the observed low star formation efficiencies in nearby molecular clouds, where individual supernova remnants can be resolved and their energy deposition into the surrounding gas measured directly. In the early universe, where gas densities were higher, metallicities were lower, and the interstellar medium structure was different, the same physical process may operate differently, perhaps less efficiently in limiting star formation, because the denser gas confines supernova remnants more effectively, or perhaps more efficiently, through radiation pressure from the more intense ultraviolet radiation fields. The appropriate calibration of stellar feedback in the early universe regime is not established from observations, and the range of plausible implementations spans more than an order of magnitude in the resulting star formation efficiency. New simulation programs specifically designed to explore the early universe regime with higher resolution and updated physics have been initiated in response to Webb's findings. The FLARES simulation, which targeted overdense regions of the early universe where the most massive early galaxies are expected to form, showed improved agreement with some aspects of the Webb galaxy population, but still underpredicted the abundance of the most massive systems at redshifts above 8. The First Light simulation, targeting individual galaxy formation in the first billion years with resolution sufficient to resolve individual star-forming clouds, reveals star formation occurring in conditions qualitatively different from the present-day galaxy regime, with higher efficiencies, more compact spatial distributions, and stronger coupling between star formation and the thermal state of the surrounding intergalactic medium. These high-resolution early universe simulations provide theoretical guidance for the qualitative direction of the required revisions. But translating their results into updated prescriptions for large-volume cosmological simulations that can be compared statistically with Webb's deep-field galaxy counts and mass functions remains an ongoing and unsolved challenge. The simulation crisis has also stimulated re-examination of whether the Lambda CDM initial conditions themselves, the primordial power spectrum of density fluctuations that seeds all subsequent structure formation, need revision at small scales. If the primordial power spectrum has more power on small scales than the simple scale invariant Harrison-Zeldovich spectrum that Lambda CDM assumes, more small dark matter halos would form earlier, providing more sites for early galaxy formation and potentially explaining the excess massive early galaxies without requiring changes to the star formation physics. This possibility is constrained by the CMB measurements, which determine the primordial power spectrum on large and intermediate scales with high precision, but remains largely unconstrained on the small scales most relevant to early galaxy formation. Webb's population statistics are now beginning to provide the first observational constraints on the small-scale primordial power spectrum from the galaxy distribution, adding a new dimension to the theoretical parameter space that models must navigate to simultaneously satisfy all available data. What the next generation of observations will establish. Webb's early universe science program is ongoing. The observations released and published through 2024 represent the first 2 years of a mission designed to operate for at least 10 years, and the most powerful scientific conclusions from the mission, those based on the largest, most well-characterized samples with the most complete spectroscopic follow-up, are still years away. Understanding what the next generation of observations will add requires understanding both what Webb still has to do and what other facilities are coming online to extend and complement its science. Within Webb's own program, the most critical outstanding need is spectroscopic completeness. The photometric surveys that have identified the anomalous high redshift galaxy populations are statistically robust, but depend on photometric redshifts and stellar population model fits that carry systematic uncertainties not present in spectroscopic measurements. The ongoing NIR-SPEC spectroscopic programs within JADES, JADES GTO, PRIMER, UNCOVER, and other approved programs are systematically obtaining spectra of thousands of photometrically selected targets, confirming or revising their redshifts and providing direct physical characterization of their gas properties, star formation rates, chemical abundances, and kinematics. The spectroscopic sample will be the definitive data set for testing galaxy formation models, and its construction is proceeding at a rate determined by Webb's available observing time and the competition from other programs across the observatory's science portfolio. On the ground, the extremely large telescope currently under construction in Chile will provide a 39-meter primary mirror optimized for near-infrared and optical spectroscopy. The ELT's Harmony Integral Field Spectrograph and Mosaic Multi-Object Spectrograph will be able to obtain higher signal-to-noise spectra than Webb for the brightest high redshift targets, measuring chemical abundances, stellar velocity dispersions, and resolved kinematic maps with unprecedented detail. The combination of Webb's unmatched sensitivity for faint source detection and spectroscopic redshift confirmation with ELT's superior spectral resolution and signal-to-noise for bright source characterization will produce a qualitatively more complete physical picture of early galaxies than either facility alone. The Square Kilometre Array will provide complementary radio and sub-millimeter observations that probe the cold gas reservoirs in early galaxies, the molecular hydrogen and carbon monoxide that directly trace the star-forming fuel, at sensitivities that are currently achievable only for the most exceptional nearby objects. Direct measurements of cold gas masses and gas fractions in high redshift galaxies will test the hypothesis that elevated gas fractions are responsible for the anomalously high early star formation rates, and will provide the observational foundation for testing modified gas physics prescriptions in simulations. The Nancy Grace Roman Space Telescope, with its wide-field near-infrared imaging capability covering areas 100 times larger than Webb's single pointing, will extend the statistical sample of high redshift galaxies by orders of magnitude, providing the large volume surveys needed to characterize the rarest and most extreme early objects, and to measure the large-scale clustering of early galaxies as a probe of the underlying dark matter structure. What Webb has actually shown us. After 2 years of science operations and thousands of published papers, the James Webb Space Telescope has established a body of observational findings about the early universe that is now sufficiently mature to support a clear summary of what has been learned and what remains uncertain. The findings are not tentative. They have been confirmed across multiple independent surveys, analysis teams, and observational methods. The uncertainties are not about whether the anomalies are real, they are, but about what physical processes are responsible for them and what revisions to the standard framework are required to accommodate them. Webb has shown that the early universe contained more massive, more luminous, and more structurally organized galaxies than any version of the Lambda CDM model predicted for the first billion years of cosmic history. The excess of stellar mass in early galaxies, the population of compact red objects that are either extremely massive galaxies or extremely massive black holes or some combination, the organized disk morphologies at redshifts where only irregular clumps were expected, the elevated star formation rates and efficiencies, the rapid chemical enrichment by early stellar generations. These are all established observational facts, not preliminary hints. Webb has shown that supermassive black holes are far more abundant in the early universe than pre-Webb observations indicated, and that their masses and growth rates are in tension with standard models of black hole seeding and Eddington limited accretion. The little red dot population has revealed a class of compact, red, apparently very massive objects with no close analogue in the lower redshift universe and no satisfactory theoretical explanation in any current framework. The reionization of the intergalactic medium was more inhomogeneous and proceeded more rapidly in overdense regions than standard models predicted, driven by galaxy populations that were already assembled in the first 500 million years. Webb has confirmed that the Hubble tension is real, not a dust correction artifact, not a Cepheid calibration error, and that the universe is expanding faster today than the Lambda CDM model, calibrated against the early universe, predicts. This is the most fundamental finding of all, because it implies a gap in the physics of the model itself, rather than merely in the implementation of galaxy formation within it. Something is happening in the expansion history of the universe between the CMB epoch and the present day that the standard model does not describe. What that something is remains genuinely unknown. What Webb has not shown is that the Lambda CDM framework is wrong. The Big Bang happened. Dark matter exists. The cosmological constant drives acceleration. These conclusions rest on foundations far broader and far more robust than any single telescope's findings can displace. What Webb has shown is that those foundations support a building whose upper floors, the physics of galaxy formation, and the detailed description of the universe's expansion history need substantial renovation. The renovation is underway. It will take years and will require contributions from Webb, from ELT, from the SKA, from Roman, and from theorists developing new frameworks for understanding the physical processes that shaped the universe's first billion years. The standard model is not broken, it is being completed, and Webb is showing us, with unprecedented precision and depth, exactly where the completion needs to happen. The scale of our ignorance. There is something clarifying about the experience of building the most powerful telescope in human history, pointing it at the universe, and finding out that the universe is stranger than predicted. It would have been reassuring if Webb had confirmed the standard picture. If the first galaxies had turned out to be small and irregular and sparse, exactly as the models expected. It would have meant that 60 years of theoretical work had correctly anticipated what the universe did in its earliest and least accessible epochs. But that is not what happened. What happened is that the universe, as it has done repeatedly throughout the history of scientific observation, revealed itself to be richer and more complex than the best available framework described. The galaxies of the early universe are not what the models expected. They are more massive, more organized, more chemically evolved, and more numerous at the most extreme masses than any simulation running on the world's largest supercomputers predicted. The black holes at their centers are more massive and more abundant than the standard theory of black hole growth allows. The universe is expanding faster than the physics of its early history, measured with extraordinary precision, predicts it should be. None of these findings are measurement artifacts or preliminary results that might dissolve under scrutiny. They have been scrutinized and they have survived. What they reveal is the scale of what remains unknown, not as a failure of science, but as a measure of how much the discipline has progressed. 50 years ago, astronomers did not know whether galaxies outside the Milky Way existed. 30 years ago, the evidence for dark energy had not yet been gathered. 20 years ago, the statistical properties of the galaxy population were uncertain at the level of an order of magnitude. Webb has pushed the frontier of direct observation to 300 million years after the Big Bang, and found that the models built from everything learned in the preceding decades do not correctly describe what happened there. That is not a defeat. That is precisely what progress looks like. The scale of our ignorance has been measured with unprecedented precision. Its location has been identified, and the instruments needed to reduce it are being built and deployed. The universe is 13.8 billion years old and observable to a radius of 46.5 billion light-years. In that vast and ancient volume, Webb has provided humanity's first genuinely clear view of the first few 100 million years, a sliver of cosmic time that, in the 300 million years it spans, apparently accomplished more than the standard model said was possible in a billion. Understanding how that happened is the central question of observational cosmology for the next generation. The answer will require new physics. It will require revisions to theories that have been trusted for decades. And it will require more observations, deeper, wider, across more wavelengths and with more instruments, that continue the process Webb has begun. The universe is not behaving as expected. That is the most important thing Webb has told us. And the appropriate response is not discomfort, but the recognition that this is what discovery always looks like. Not confirmation of what was already known, but the revelation of what was not, and the beginning of the long, difficult, necessary work of understanding it.